A buffer solution consists of a significant amount of a weak acid and its conjugate base. Let's say we have a generic weak acid HA and its conjugate base A-, and we're going to use some particulate diagrams to try to understand how buffers work. So for our first particulate diagram, let's count out how many particles we have of each. So first, let's count how many HAs we have. So there's 1, 2, 3, 4, 5 HAs. And there's also, for A-, there's 1, 2, 3, 4, 5 A-. And when looking at a particulate diagram of a buffer, usually water molecules are omitted for clarity. And also keep in mind that this particulate diagram is just meant to represent a small portion of the solution, so we can get an idea about what's happening in the entire solution. Also notice that like water molecules, cations are also left out of the particulate diagram. So we have 5 HA particles and 5 A- particles in our aqueous solution. Having equal amounts of a weak acid and its conjugate base is a good buffer solution. Let's see what happens to the buffer solution if we add in a small amount of acid. So here I'm drawing in an H+ ion, and let's think about adding this H+ ion to our buffer solution. When the H+ ion is added to the solution, the base that is present will react with the H+ ion to neutralize it. So the added H+ reacts with A- to form HA. So for the particulate diagrams, this added H+ is going to react with one of the A- present in the buffer solution. So the H+ and the A- form an HA. So we're going to go from 5 HAs to 6 HAs. So let's look at this next particulate diagram here. We can see there are now 6 HAs in the solution. So let me write down 6 here. And since we started with 5 A- and we lost 1, we should have only 4 A- in solution now. So let's write down a 4 here. So you started off with 5 HAs and 5 A-, and upon the addition of a small amount of acid, the acid was neutralized by the base that was present, and we formed 6 HAs and 4 A-. So a buffer solution resists changes in pH, so the added H+ was neutralized by the presence of the base. If the buffer solution had not been present, if we just had some water and we added some H+, the pH would have changed dramatically. One way to write the acid-base neutralization reaction that occurred is to write H+ plus A- goes to HA. However, since H3O+ and H+ are used interchangeably in chemistry, we could have also written the net ionic equation as H3O+ plus A- goes to HA and H2O. Next, let's go back to our middle particulate diagram with 5 HA and 5 A-. And this time, let's try to add some hydroxide ions to the solution. So think about, let me go ahead and draw an arrow here. So we're going to add a small amount of base to our buffer solution. The hydroxide anion will react with the weak acid that is present, HA, to form H2O and A-. So for the particulate diagrams, we can think about this OH- reacting with one of the HAs to form H2O and an A-. Since we're using up one of the HAs, we're going to go from 5 HAs down to 4 HAs. So let me write down here 4 HAs. And when this HA reacts, it's going to turn into an A-. So we're going to go from 5 A- up to 6. So let's count them over here. 1, 2, 3, 4, 5, 6. So let's write in 6 A-. If there was no buffer present and we're just adding hydroxide anions to water, the pH would change dramatically. However, with a buffer present, since there is a weak acid HA present to neutralize the added hydroxide anions, the buffer solution resists a change to the pH. So let's summarize how buffer solutions work. If we add a small amount of an acid, H+, to a buffer solution, the conjugate base that's present, A-, neutralizes the added acid. Therefore, the buffer solution resists a change in pH. And if we add a small amount of a base, the weak acid that's present will neutralize the hydroxide anions. Therefore, the buffer solution resists a change in pH. Let's say we have an aqueous solution of acetic acid and an aqueous solution of sodium acetate. And let's say we have equal moles of acetic acid and of sodium acetate. Mixing these two solutions together would form a buffer solution. To understand why this forms a buffer solution, let's first think about acetic acid. Acetic acid is a weak acid and only partially ionizes an aqueous solution. Therefore, in aqueous solution, we have mostly acetic acid, CH3COOH. Sodium acetate is a soluble salt, and it dissociates completely in aqueous solution. Therefore, in aqueous solution, we have sodium cations and acetate anions, CH3COO-. The acetate anion is the conjugate base to acetic acid. Therefore, in aqueous solution, we have a weak acid and its conjugate base, and so we have a buffer solution. If we try adding a small amount of acid to the buffer solution, the conjugate base that's present will react with the acid and neutralize it. So in the balanced net ionic equation, the added acid, hydronium ion H3O+, reacts with the acetate anion to form acetic acid and water. So the added hydronium ion was neutralized, and the buffer has resisted a dramatic change in pH. If we try adding a small amount of base to the buffer solution, the weak acid that is present will neutralize the added base. So in the balanced net ionic equation, hydroxide anions react with acetic acid to form the acetate anion and water. So the added base was neutralized. So to summarize, the acetic acid acetate buffer system resists dramatic changes in pH when small amounts of acid or base are added. And I just noticed I forgot to include the L for liquid for water in the balanced net ionic equations.